So we lost one participant. Where is Gregor? Gregor, are you with us?
Screen sharing,
yes.
but he's
Just a second.
now. Hmm?
Now. Hi,
Yeah,
Gregor.
I was seeing you.
Yes, but from the backstage. Now it should be.
I was in the backstage.
Yes, now we are live. So hello everyone. Our next session explores edge AI in automotive cybersecurity, and it's enabling context-aware threat detection directly in the vehicle, on vehicles' computing systems. This approach is critical for protecting cyber security of vehicles, software-defined vehicles in general, while addressing challenges in resource-constrained environments. So our context. Joining us from week one are Gregor. He is a senior cybersecurity solution architect with over 15 years of experience building defense systems for zonal architectures, IVI, T-Box, ADAS systems. And Christoph, senior cybersecurity engineer specializing in automotive system and software cybersecurity, and the technical R&D representative. He's also the technical R&D representative for projects like IDPS and VSOC platforms. So please welcome Gregor and Christoph to the stage. The stage is yours.
Thank you much, Sergey. And good day, everyone. And thank you for joining us today. We'll be diving into a critical, fast-evolving topic, edge AI in automotive cybersecurity. And the aim is to explore the challenges that we face, that we see, share some insights from our engineering works that we have done in the past with our partners and customers, and the opportunities that we see are ahead in front of us, and how intelligent vehicle embedded system solutions are reshaping the future of automotive security. With me is Christoph, senior solution engineer. He will introduce briefly himself. And I'm the senior solution architect in week one, joined with Chris, and together we bring you this topic into an overview about our researches that we have done. And Chris, feel free also to say some words about yourself.
Yeah, so I feel like I've already been properly introduced by Sergey, but just in case, hi everyone, once again, my name is Christoph. I'm working here at VicOne as a senior cybersecurity engineer, most responsible for the research and development projects that we have in Europe. Also, as my background, I'm a system and software developer of now over 6 years of experience working for both tier ones and OEMs. Nice to have you all here.
All right, just brief introduction for those who don't know our company that we both work for. VicOne has been launched in 2022 as an automotive cybersecurity provider. We may be new, but as a subsidiary of an industry giant and threat intelligence expert, Trend Micro. It's an IT enterprise company. We inherit decades of threat intelligence, and our team not only understands cybersecurity, but also the embedded systems in the automotive environment, automotive software that is being used, which is traditionally not a specialty of an IT company. So we can create, as VicOne, cybersecurity solutions for you and the automotive industry. And addition, oops, there's an automated turnover. I need to stop this. We are fully funded by Trend Micro. Our strong financial health allows us also to continue investing into the development of automotive-related technologies while remaining neutral, which is also very important in this cybersecurity market. And I would like to start the session with a question to the audience, which are basically the pain points probably you may also be facing. So no need to give any response here in the chat or so. We don't have a live Q&A later on anyway. But if you see any of these challenges in your operations, either it's in the VSOC or is it in the daily work that you are doing, what we see is basically that the rising cloud storage and transmission costs are becoming unsustainable. And especially with the volume of the modern data vehicles generate, we know that the car is able to generate tons of data. We see also that false positives are overwhelming the security teams, making it harder to focus on the real threats. And perhaps also most critically, distinguishing between a cyber attack and a system malfunction is still incredibly difficult. So what we hear from VSOCs teams they are handling sometimes issues that are, oops, there's another strange that's jumping over. They see basically that there are reports generated or events generated that are coming from system malfunction, not really from a cybersecurity point of view. And at the time, basically, it's also a time-consuming process, evaluating the threats on the device, fine-tuning the models in the cloud, and it's clear that these traditional approaches are struggling to keep up. These challenges that we see aren't just technical ones, they are also operationals, financial related and strategic, and they demand a new approach, which we would like also to show you in this presentation. And first of all, let's look at the typical cloud-only security workflow. So cloud-only means you have a VSOC, probably an XDR platform in the cloud, in the OEM's backend, for example, where all the security events are being uploaded, all the security logs, all the network traffics, maybe device telemetry data like GPS coordinates, this kind of stuff are being uploaded. Maybe your debug information from your systems that are generated. And then in this, once they are uploaded and they are pre-processed in the cloud, we train the baseline detection models. And this detection happens continuously. But when false positives spike or new threats emerge, we need to retrain the model. And this cycle is slow, pretty expensive. We need a lot of resources to perform this process, and increasingly inefficient. So cloud-only strategies are hitting their limits, what we see. And the latency, especially until you can react on an incident or until you get even the relevant data, the cost of uploading this massive data from, imagine, hundreds of thousands of vehicles or millions of cars, and the lack of real-time responsiveness make it even unsuitable for the dynamic nature of modern vehicles. And this is why we need to also rethink where intelligence lives, either in the backend or in the car. And this brings us to the Edge AI topic of today. And we see that the threat landscape, and we have seen also in the introduction session today morning, that the threat landscape is expanding rapidly. We see hundreds of vulnerabilities that have been reported in automotive systems, ranging from the data theft topics, but also device hijacking, to complete loss of service availability. And these aren't any more theoretical risks, they are real. They are growing and they are documented. So you can see these issues very well in the public as well. And our research, combined with the data from the NVD, shows a clear trend as vehicles become more and more connected and software-driven. We know these SDV topics today. The attack surface grows exponentially. And with every new feature, every new integration, we are introducing new potential entry points for attackers. And we are witnessing a transformation in vehicle architecture. So from traditional vehicles to connected platforms, and now to software-defined vehicles powered by Gen AI. And these aren't just cars, they are living platforms, continuously updated and intelligent. And OTA updates, AI-driven features, and cloud integration means that vehicles are no longer static, they evolve over time. And this evolution brings incredible opportunities for innovation on one side, but also introduces unprecedented complexity and security challenges. And in this paradigm, cybersecurity must evolve too. So the static defenses won't cut it, and we need adaptive, intelligent, and embedded solutions. And let me show you one example about the comparison of different systems, because when these vehicles evolve, so also their requirements evolve, and not just incrementally. While a traditional ICE-based engine we might have around 100,000 requirements, mostly mechanical, relatively stable. And with electric vehicles, we have seen battery systems, terminal management, software interfaces coming in, doubling that to over 200,000 requirements. But with the SDVs, we are talking about 500,000 plus requirements. And for an autonomous vehicle, over 1 million. And this aren't only numbers, they are representing design, the implementation, the testing, the traceability, and the validation tasks. And every new feature, every new OTA update, every AI-driven function adds layers of complexity. And with that complexity comes the risk, longer testing cycles, more dependencies, and higher chances of missing something critical. And this is why cybersecurity must also be integrated, not bolted on, and why automation intelligence are essential for this topic. And in the past, security boundaries were pretty well defined. So you could draw a perimeter around a vehicle system and protect it, but today the perimeter is gone. So features, they vary by region. We saw it also in one of the presentations today morning that we have different requirements, different features in different areas and regions, by the customer itself, even by the subscription tier. And OTA updates also change the functionality overnight. And then AI also introduces decision-making that's not always predictable. And these vehicles are now connected to everything, right? To the OEM servers with the backends, with service providers, with mobile apps, with cloud services, even hotel and restaurant Wi-Fi. And this attack surface is dynamic, constantly shifting. And that means also that yesterday's security assumptions may not apply anymore today. So we need to real-time visibility as well, kind of adaptive defenses, and continuous monitoring because the threat landscape is no longer static as well. So here's the big question: that can traditional security risk management keep up with this pace of change? And the answer is unfortunately is no. So static processes can't handle dynamic environments, and manual testing is too slow. And with AI and OTA driving constant change, the black box decisions make it harder to predict and mitigate these risks. So when we need now a new model, ones that continues, automated, and built for the realities of the SDVs and autonomous vehicles. And that's where closed loop security comes in, which I would like to present in a quick block diagram. Closed loop security risk management is our answer to this challenge, and it's a unified platform that continuously monitors, learns, and adapts. And it integrates feedback from the vehicle, from the cloud, and the security operations center. And it's not just only about detecting the threats, it's also about understanding them in the context, responding in real time, and improving over time. And this framework is inspired by the MITI SDV system architecture. I put the link to the PDF in the bottom of this presentation that will be shared after the event. And it's designed specifically also for evolving vehicles, not the static ones. It's how we move from reactive to proactive and from fragmented to unified. And here's the key shift. We need to move intelligence now to the vehicle. In the traditional model, how we approach cybersecurity for today, the inference happens in the cloud. That's powerful, but it's also slow and very expensive. So think about the cloud costs, think about the data upload transmission costs of 1 million cars. Every vehicle uploads massive data permanently without, if there is an incident or no incident, the data is uploaded. So this is what we want to address with Edge AI. And inference will happen now in the vehicle and right where the data is generated and where the decision needs to be made instantly. And the aim is basically to reduce the latency, cut the cloud costs, and enable real-time threat detection. And it's not about replacing the cloud. It's also about complementing it with a smarter, more faster, and local intelligence. And this is also the foundation for a truly resilient, self-defending vehicle. And having made this introduction, I would like to hand over to Chris, who would walk us through the basic concept. And we will also follow with a demo about this Edge AI topic. and close with a roundup session of what we have been discussed. So Chris, if you can, I will continue sharing the screen. If you just let me know when I should jump over to the next slide. And sorry that the screen jumps over, let's say, dynamically alone without my interaction. So I will probably have some back and forth slide change.
Yeah, no worries. So thank you once again very much, Gregor, for the introduction to the topic. And now that we have all the basics covered, it's time to introduce one of the most powerful capabilities of Edge AI, which is the real-time threat recognition. The way we do it is that with the help of the NPUs, which are the neural processing units embedded directly in the vehicle, we have the ability to perform inference locally, right where the data is generated. This is something that Gregor has already mentioned before. The main goal here is that you could have pieces of event data or something that's related to your current threat intelligence split between different ECUs in your vehicle. And by themselves, they don't really mean much, but once you contextualize this, once you send it over to a central processing unit and put it into context, this is when it starts to make sense. And what this means that when a known attack pattern is detected, the vehicle can immediately recognize and trigger an alert without waiting for the cloud-based analysis. So all the actions that you normally have to take only after the upload has already been finished to your VSOC platform and analysis has sat down and gone through all the details, all of this, at least on the recognition level, can happen already in the vehicle. And this leads to drastically reducing latency, and it enhances the responsiveness of the overall system. Where it's especially critical is that in scenarios where the detection data comes from different ECUs, the data by itself might not really be useful. It has to be all put together. This enables also the vehicles to act autonomously in the face of threats and reduces the dependency on centralized infrastructure. This also helps mitigate the risk of delayed responses due to connectivity issues. So in case if the user doesn't have the ability to perform an upload of the data, let's say if an OEM or the car operator just simply cannot upload the data, doesn't have an access to the diagnostic station if the data has to be uploaded through a physical interface, this then enables us to do the first and the most crucial steps of the analysis already on board. And from our perspective, it's not just a technical upgrade, but it's also a strategic shift in how we think about automotive cybersecurity, because up until now, it's always been reliant on having to collect all the data, then upload it, and then have to sift through it and just look and try to make sense out of it. And the way we do it currently is we already have a massive backlog of the threat intelligence and the event data we've collected, and we can now deploy it on board and do the analysis there. What it also does is empowers the vehicles to become active participants in their own protection. So you don't need to have any human interaction here. And what it ultimately does is it contributes to a safer and more resilient mobility. Let's get the next one, Gregor. Okay, yeah. So here we take the concept of real-time detection a step further towards self-defending vehicles. And the way we do it with Edge AI is that the vehicles, from our perspective, are no longer passive endpoints waiting for instructions. They become intelligent systems capable of learning from past incidents, recognizing emerging threats, and taking defensive actions autonomously. This means that they can isolate compromised components, adjust behavior, alert the driver, all without the external input. The way we see it is that the autonomy is especially valuable in disconnected environments or during high-speed operations where cloud latency is unacceptable. It also reduces the burden on backend system and security analysts that would normally have to, as I mentioned, just search through the data, analyze it first, and then come up with a conclusion about what happened. By embedding intelligence directly into the vehicle, we create a new layer of resilience where these vehicles can adapt to the new threats as they emerge, making them future-proof against evolving attack vectors. Yep, it's good. Let's get to the next one, Gregor. Okay, so now time for the deep dive into our patent pending technology, which is the X-Carbon Edge AI. One of the biggest challenges in automotive cybersecurity is how fragmented the data is across multiple ECUs. You might have a log collector or an IDPS deployed in several of your high-performance computing ECUs in the car, but it doesn't mean that all of them will be communicating with one another and exchanging this data and correlating what happened. This will usually just be a separate event generated on a single ECU, which is kept in a log and then uploaded and then analyzed in the VSOC. And Edge AI solves this by correlating the telemetry and security events across all these units and creates a unified view of the vehicle security posture. And it doesn't just collect data by itself, it transforms it into contextualized attack paths. Because we know how the attacks normally happen, we have threat intelligence knowledge, and we have previous experiences with the security events, which tell us how the attacks normally happen. We can create models of the attacks, or we understand how they normally happen, which leads us to being able to also detect how they happen on board. And also by creating these paths, we understand how the threats propagate through the system. So an attack might happen at a certain point, it then spreads through the system, it ends at, let's say, a high computing ECU, and this is something we're able to detect. An important step here is also that the Edge AI compares these paths with real-world incidents. So on top of the regular vulnerability analysis and the threat intelligence research that we do, we also look into how the real-world incidents that were disclosed have happened, what attack paths did the attacker take, and how we could have possibly prevented them. And based on that knowledge, we then develop the models that we deploy on board. This, in the end, having all of this data as a background, we massively reduce false positives and improve detection accuracy. It also enables predictive capabilities, allowing to anticipate potential attack vectors before they're even exploited. So if we know exactly how an attack would happen, we can implement the preventive measures that will make it never happen in the first place. And by embedding this intelligence at the edge, we ensure that vehicles are not just reactive, but proactive in a way that they can defend themselves. Okay, let's go on, Gregor. And now, how do we do it so that the models that we develop and we deploy are always up to date? From our perspective, cyber threats are not static. They evolve constantly, and our defense models must evolve with them. And here we'll outline how we keep our Edge AI models up to date using a continuous learning loop. So first, what we do is we gather threat intelligence, all the event data that I mentioned, and transform incidents into TTPs, so tactics, techniques, and procedures. So basically how the attacks happen. And then these TTPs serve as the foundation for the fine-tuning of our AI models. Once refined, the models are then thoroughly tested and validated to ensure the reliability in the target operating system. Then, once the testing phase concludes, we can deploy them into the vehicles via OT updates, ensuring that the protection is there without having to do any manual intervention from the operator's perspective. System models are usually quite large by themselves. We also have the ability to only update a subset of detection rules instead of the entire model. So if we, let's say, detect that there was an attack that happened that we could have prevented, and we know exactly what the attack path was and what components were affected, we have the ability to only update this part of the model that takes care maybe of a specific communication interface. And this process ensures that the vehicles are always equipped with the latest defense mechanisms. And it also allows us to respond quickly to the zero-day threats and emerging vulnerabilities, since the upload time and the update time is really just as quick as us developing the update and sending it through OTA. And the key here also is automation, because manual updates are too slow for today's evolving landscape. Which also leads us to the next slide, Gregor. Yeah, which is how we achieve this automation and quick update and response times using the SOFI architecture. So this is an architecture modeled, developed by ARM, where we are a partner. And what it does, it provides a cloud-native framework for developing and deploying automotive workloads, including AI models. Normally, how it would happen is that whenever we develop a change, this would have to be tested in a real-life environment. So you would have to have a physical ECU, entire operating environment, including the peripherals. Then you would have to upload it, test it, have like a workbench where all of it comes together. And this is not only a lengthy process, but it's also very reliant on the availability of the hardware. When you have distributed teams where engineers work from different countries, even this becomes increasingly difficult. So what the SOFI architecture allows us to do is to fine-tune the models in the cloud and then test them on these virtual simulated devices, which eliminates the need for physical hardware during development. And this by itself not only increases the update cycle time, but it also reduces the cost because you do not have to purchase the physical components themselves. It also ensures that the models are validated across diverse configurations because all of them can be simulated and tested beforehand and then deployed. It also improves the reliability by catching edge cases early in the pipeline, since this is where the automation comes into play. The entire process is integrated into a DevOps workflow. So this is the training, validation, deployment. All of this can be put into a, let's say, single pipeline, where each step then is verifiable, interchangeable. So that's if the developers, let's say, want to introduce a change at an early stage, they don't only have to wait for the hardware testing to be done, but they can introduce the changes as the pipeline goes on, and whichever change they introduce will be then later verified. And this cohesion ensures that the updates are fast, resilient, and traceable. From our perspective, it was really the best way of moving forward, because sticking to the old school way of doing things, which was develop some change, train our models or test it, then deploy it on the physical device, wait for the physical device testing to be done. This is really restrictive for the developers, since they had to, as I mentioned, they had to wait for the physical device testing to be done to collect all the feedback, which could be a lengthy process, and only then they could come back to the initial step of the pipeline. And the way we do it now is that we can collect the data as we go throughout the pipeline without having to wait for all the physical testing to be done. Okay, Gregor, I think that's we should now jump to the demo. So now we will move from theory to practice with a live demo. Demonstrate is how the edge AI that me and Gregor have introduced operates in a real world scenario. So you'll see how the vehicle detects a threat, triggers in-vehicle alert. You'll see how it synchronizes with the VSOC, and it will also highlight the speed and accuracy of the detections. So Gregor, on to you.
Yeah, I just put another slide here in the quick from today morning, just a picture of the setup. It's basically an IMX95 board, what you see here on the left side, which represents our target ECU system, which operates Linux environment, some applications over there. You see there is an Ethernet connection to my Wi-Fi router, which is also connected to a Raspberry Pi through the yellow Ethernet cable here. The Raspberry Pi has the simple task. It represents kind of backend system. It could be from the OEM, where I run kind of log visualization tool to see basically the logs, the final detection logs coming from the system running on the IMX95. What I would also like to say is that this system has been enhanced with the IDS from our technology, and also leverages some other events. Let's just basically demonstrate it here in the block diagram. Not only the network and CAN IDS events are being fed into the system, but also system telemetry like CPU load, memory load as an example. And we will demonstrate two prompts basically. Typically, this could be also a prompt that you do in your backend, where you say, okay, I have a data set. Please create with this data set a structured incident report following the format provided below. And you have basically, I want to see the incident detail. I want to see the attack scenario, the system logs impact. I would like to have an understanding about the CPU log impact, the memory logs, the network, and the CAN bus impact. And please ensure, this is what I tell the LLM basically, that this data includes real-world exploit information, relevant CVEs, specific log impacts for CPU, memory, network, and the CAN bus. And then there will be another prompt. What you will see is basically saying, please provide the related incident ID of the following data. Give general answer if no related incident is found. Out of this LLM, the report will be then sent to my Raspberry Pi in this case, but could be then basically the OEM's backend, which will basically display the report in the VSOC environment, in the SIEM environment of the OEM, which then basically can be analyzed by the VSOC analysts to understand what's going on specifically in this vehicle. And let me now quickly jump to the dashboard. So this is the kind of visualization tool that we developed, which we use not only for our ideas, but also from our smart cockpit, which is a different topic, but we basically display the logs once they have been analyzed by Edge AI. They will pop up and show up here. And I also have a connection to the IMX95 boards from my computer, which has basically representing the attack scripts that we will execute and also generate basically high CPU load. We will consume some memory. We will send some Ethernet network traffic, some traffic on the CAN bus will be generated. And then we will ask the LLM basically, which has been fine-tuned with our threat intelligence, to give us a little bit of insights what's going on in this particular ECU. So let me start. It's very simple attack script called attack.sh, which basically now starts the process. It's initialized the Llama system, and you see basically already here in the background in some data is being basically sent to the backend, which I just wanted to do some, for visualization. So that's basically user input data or the CAN bus input data, which basically represents the CAN bus traffic. And already what you see here that the LLM already started to think. I slowed down a little bit because you see there's already the second prompt going on. We will let it running through because it takes kind of 2-3 minutes with this delays here. But we can already start analyzing the results from the first prompt. If you remember, it was basically creation of the first analysis for each of the issues. And let me just scroll up a little bit where I started the attack. Is basically here. We have the user. Here is basically the first prompt. So that was basically the first prompt was saying create a data set of structured incident reports following this specific format. And now we see basically the first analysis has been done about the network interface data summary starts here. So what we see basically with all the simulation that we have done on the network, that this log indicates that there is potential anomalous behavior on the Ethernet 1 interface with some significant fluctuations in the received and transmitted bytes, along with some increased error counts. And this suggests possible network congestion or a network attack, right? So we are at the moment see some anomalies. There is a reasoning for this because the log shows a mix of operational states for two network interfaces, Ethernet 0 and Ethernet 1. Ethernet 0 interface is consistently down for the duration of the logs, while the Ethernet 1 is showing fluctuations in operation states, including some periods of being up and down, and this key metrics node basically includes substantial increases in the receive bytes, in the transmit bytes, in the errors, and on the Ethernet 1 interface, particularly between the timestamps this and this time, right? And there's also kind of mentioned that there is noticeable spikes in the error counts, which suggests potential network congestion or issues possibly indicating abnormal activity. And these multiple entries show also receive packets and transmit packets remaining constant while the byte count fluctuates significantly. And considering this continuous fluctuations in the traffic metrics and the error counts, this log indicates a potential anomalous behavior on the Ethernet 1 interface, which may signify a network attack or congestion. So this was the first analysis. We also saw on the CAN bus frame that there was basically an entry with the identifier, the following here, appears to deviate basically from the regular message structure, indicating a potential anomaly on the CAN bus as well, and the reasoning about it. We don't need to go through that because we will see it in the back channel as well. I will jump over a little bit down to the process about the, let me double check if it finished the analysis already. Yeah, it's done already. right? So let's go now what the, let's say the VSOC analyst now received. The output from the LLM was, this was basically posted now to the Raspberry Pi. I have here from the web browser connection to my Raspberry Pi for this dashboard here. And we have basically the summary of the network interface analysis with all the basically what we just described, the error counts with the transmit sessions, etc. We have also a CPU log impact example, which was basically an exploit code or process with a very high CPU usage, which indicates basically an exploitation potential. And this excessive consumption of system resources could impact overall performance of the system, raising concerns about malicious activity within the system. We also done this CAN bus analysis with basically deviation for this CAN ID 001 with an unexpected message from this PID. And we saw also that this regular operation data typically associated with this ID was indicated a consistent message structure. But there was a sudden appearance of anomalous messages, suggest potential concurrency or unauthorized use, raising further concerns about the system stability. And then you have basically the impact example here. And the reasoning is basically that there are irregular messages from CAN1 that indicate potential communication issue or abnormal activity within the system, warranting further investigations to determine the legitimacy of the process attaching to this CAN ID. And very similar for the memory lock, because when there's a process consuming so much processing power, typically also memory usage goes high. We consume right now 63% of roundabout of the memory. And this means now also that there is a process detected. We call the dirty cow exploit. Could be any process that consumes so much memory. And the LLM was basically analyzing this telemetry information, the telemetry logs, and says that this very similar to the CPU analysis, this high memory and CPU consumptions by this process suggest a potential exploitation attempt. An anomalous resource usage could significantly impact the memory availability if that continues to grow like this, and further highlighting the concern for system integrity. What is more important, the second prompt, because if you remember, we were asking, I will just switch back, to provide the related incident ID of the following data, give a general answer if no related incident is found. The answer for this was that this related incident ID for this exploitation of vulnerabilities in BMW vehicles, probably some people know the Keen Security Labs from Asia, is this incident number. And this incident highlights the successful compromise of several BMW models, infotainment and telematics systems for both physical and remote methods. And we have now an indication that these detections that have been processed now on the ECU are not coming from a malfunction, but have a very high likelihood that they are real incidents that require further analysis of the vehicle logs. So only now, when the VSOC analyst sees this summary, which would he normally perform by his own manually or in his cloud, now he gets basically the trigger that this vehicle has some problem, right? And typically the process would be that the VSOC analyst now would grab from this particular single vehicle all the security logs, all the debug information that is necessary to narrow down the issue, to make the triage and to perform necessary actions if required. And having said that, I would like to switch the presentation to Chris with some final words. Chris, if you want to take over.
Yeah, sure. So then, let's wrap up this section by looking at the tangible benefits of Edge AI. So first of all, it cuts cloud data transfer and processing costs by up to 60%, which is a major operational saving for any OEM or Tier 1 who decide to use it. Second, it speeds up the analyst workflows by reducing triage time by up 80%, also allowing teams to focus on real threats instead of having to redo all the time-consuming work. And third, it filters and summarizes the security events before syncing with the cloud VSOCs, So it reduces noise and improving clarity. So instead of being bombarded with lots of different notifications and alerts, which can lead to the same conclusion, you get an already summarized output. And these efficiencies then translate into faster response times and better resource allocation. They also reduce the risk of missing critical threats due to alert fatigue. And Edge AI enables smart detections making at every level, from the vehicle to the SOC. And the way we see it, it is not just about technology. It's about strategy, efficiency, and resilience. And these results that we've shown to you validate the shift from cloud only to hybrid intelligence models. And they show that the Edge AI is not just a concept, it's a proven solution that we've developed with a measurable impact.
Thanks, Chris. So we are at the end of our presentation. We have still time for questions, I think, Sergey?
Yes. So
Okay.
first of all, I need to switch on my video. Thank you very much, Gregor. Thank you very much, Christoph, for great insights, great presentation. The participants flooded the Q&A section with questions, and
I just opened it up, yeah.
Christoph was proactive and answered already a few questions because he kept the time probably in mind. However, we have two unanswered questions, and I would like to give you the chance to address them as well. And maybe a remark to the participants. Since this chat, also the Q&A section, is not persistent, this chat and the Q&A session will be closed after this session. That means you have roughly 3 minutes left to read the answers to your questions. So go there, have a look, and in the meantime, we'll get to the other questions. So I will show the first question from SB on the stage so that you have the possibility to read it and to answer it. Here we go. How are you validating responses from the LLM? Have you explored LLM as a judge, chain of thought, or other approaches to do this?
So maybe a very basic statement. So what we now also do is developing an AI LLM model scanner, which will be an offline and onboard solution. That depends where what is the use case. This is actually also the IP and the know-how that we got from Trend Micro, our mother company, to be able to scan AI models. We use open source models, Llama 3.x, which can be basically definitely having hallucination or other, let's say, harmful intentions inside. What we do is basically we have a RAG. We don't change the model, right? Or we don't create our own model. Basically, our approach is that the OEM or the tier one can come to us with any model, what they have, or they can use our solution as is. And we have a RAG with our threat intelligence where we basically fine tune so that the LLM talks not about the God and the weather, but about cybersecurity relevance. And this was actually when you would feed the logs just into ChatGPT or stuff like that, you would say, okay, I have a beautiful CAN message here, this kind of things, right? So to avoid this, we have fine-tuned the models with our threat intel.
Good.
I'm not sure, Chris, anything to add?
Yes.
It's a very similar question to a few that we already had in chat. So mainly the validating responses from the LLM, we're making sure that there is no hallucinations, as people call it, in the outputs, so that we very selectively choose the input data, because the quality of the input data is what has the most major impact on the quality of the output data. So this is the first step. And once we've done this, so we know that the input data is good, then we put it through the model. So we train the model based on this data, and then we verify the outputs in two ways. So first of all, the outputs, or the physical output that we receive, is verified by the engineers, just to make sure that it's what we expected. And then we test it in a real environment. So we simulate a scenario which can be one of the attacks that we've analyzed before and used as an input, or something else that could normally happen in the vehicle. And we see if this model behaved in a way that we expected to under the specific scenario. If it does, then we know that the output is good.
Good. Thank you for that. I see that we got 3 more questions, and that's exactly the reason why we have the so-called lounge where Gregor and Christoph will be for the next couple of minutes. So please, Mohammed, H, Rida, and Apil, please go there, ask the question, mingle with other participants, get your question answered. Gregor, Christoph, thank you very much.
Thank you very much, everyone.
Bye-bye.
Thank you as
See
well.
you
Thank you.
and have a
Bye.
nice rest of the event. Bye.